So, welcome everybody to SUNS, the Symposium for Undergraduates in Mathematical Sciences. This is the 11th year that the symposiums run. So every year every year it has a theme. So last year was math and design, and the year before that it was math, environmental sciences. And this year it's math and game strategy and competition. So I'm Rich Schwartz. Jill Piper and I are the faculty sponsors, although the truth is we hardly do anything. So I wanted to say first that the undergraduates this year, Zev Chernolas and Nick Laurie and Ben Levesque and Levon Mohammed, these four guys have really worked tirelessly to put this thing on, and also Audrey Aguiar in the math department. So it's really these 5 people who have kind of put the thing on. The event is sponsored. It gets funding from various sources. This year, the Pure Math Department of Brown and the Applied Math Department, and also ICERM, which is Brown's new NSF-funded research institute. So the only other thing I really want to say is that the banquet is at 6:30, and it's free, and you should go. And it's basically it's pretty close to, it's on George Street, a little bit past Thayer. It's about 2 blocks from here in one direction. It's in the Chancellor's Dining Room at 6:30, so just remember that.
I'll be walking there after the last class.
Yeah, okay, people kind of follow the crowd over. So let's see, so our first talk today is by Glenn Ellison, who's the Gregory K. Palm Professor of Economics at MIT. He's going to talk about Google advertising. So.
Okay, thank you. Okay, what? Okay. Yeah, I think the mic is on, although I don't know if I need it, although I have a cold. So thank you for inviting me. I was invited to give a talk on game theory, and I should say that game theorists in economics do a couple different things. One thing that game theorists do is spend their time actually just doing math and trying to prove theorems that will be useful to economists who are trying to talk about the world. And then the other thing that game theorists sometimes do is actually try to do the economics itself and talk about the world. And I figured as long as this was giving people exposure to different areas where math is used, I figured I would actually give an economics talk here. And so this is going to be an economics talk where I'm going to use game theory, and I'm going to use game theory to talk about Google advertising. So I'm sure everyone's very familiar with Google. Google's this sort of famous success story where it started as a research project by a couple Stanford graduate students in 1996. It's now a $200 billion company. Many of you take computer science, they probably sort of teach you this sort of basic Google PageRank algorithm for organizing websites, which is just basically finding the eigenvalue of a matrix and, to sort of revolutionize the field. What I'm going to talk about today is not Google's PageRank algorithm, but something about less attention is Google's mechanism that was invented for selling advertisements on Google search pages. And this was not invented by Sergey Brin and Larry Page. People who invented it did not get famous. It was apparently invented by just an engineer who was working there and an undergraduate majoring in biology at Stanford who was there as a summer intern in one of the first summers. And I think if you look at it, I would argue that Google advertising may actually have been more important to Google's success than the Google PageRank mechanism was. Some basic facts about Google advertising. One is Google advertising produces very stable results. This may seem unsurprising, but what did advertising internet look like before Google? Well, before Google, Yahoo was the #1 internet search provider. Up here is a graph I stole from someone else's paper. That's bidding for 1 week on a particular keyword on Yahoo. Like if you want to have your ad displayed when the word auto insurance is typed in by someone. And something you'll notice about those high bids is that over the course of a week, the high bids change thousands of times. The bid starts out at $6. Over the course of 7 or 8 hours, it's climbed all the way up to $10, goes back down to $6. It climbs up and down and up and down and up and down and up and down. And Yahoo's thing, I'll come to later, just had a very hard time finding a market clearing price for advertisements, which meant that if you wanted to bid on Yahoo, you had to spend a tremendous amount of time designing an automated bidding system rather than just buying the ads you wanted to buy. That's one problem Google solved. Second thing to note about Google is Google advertising is just phenomenally profitable. You know, many of you use Google. Google's revenue per search is about 6 cents. So if you think about the number of times you use Google, on the average search done on Google, Google makes 6 cents in profit. Okay? Well, you do 6 cents, they have 150 billion searches in the US alone, and then probably an equal amount overseas. Google makes $12 billion of profit a year. In some sense, that is the key to Google's success. If you just have this machine that throws out $12 billion, you can hire all kinds of engineers and computer scientists and mathematicians to do all kinds of cool stuff. So as long as that spigot is open and 12 billion a year is flowing in, you know, you're going to be a very successful company, even if you didn't have a good page rank algorithm or whatever. This also sort of shows you why people think that, you know, someone asks, you know, like, can Google actually grow? Well, Google actually has this phenomenal potential to grow. You know, 150 billion searches a year is 1.5 searches per person per day in the United States. So most people in the United States are not like you. Most people don't really use Google much yet. So if you think about if everyone becomes someone who's using Google all the time, what could Google be worth? Could be worth $2 trillion instead of $200 billion. I mean, there's never been a $1 trillion company, but Google could be such a company. Third fact is that Google's been much more successful than other search providers in the US. You know, one example, you know, Microsoft has spent an awful lot of money on Bing. Bing has its continuous flow of negative $1 billion a year in profits. And, you know, this is sort of a big contrast. And, you know, there are, you know, I think it's notable that that's one thing I'll try to understand is why is it that Google that works so much better, makes so much more money than other search providers? It's not true in other countries. There are several countries where Google is lagging other firms. So what am I going to do in this talk? You know, I'm going to try to write down several game theory models to explain how Google advertising works, why it's successful. In doing this, I'm also just going to try to give you a sense for how it is that economists use game theory and why they use game theory. And, you know, game theorists are often asked to talk about the world. Like Google is a great example where there are big federal antitrust and regulatory questions with Google all the time. Should Google be allowed to buy Motorola? Should Google be allowed to serve Yahoo searches? Should Google be allowed to digitize books and put them up on Google Books? You know, should Google be allowed to pay? Should Google be allowed to require that Google be the default search engine on Android? Should Google be allowed to pay Dell to make Google the default search or make Chrome the default browser when you buy a Dell computer at the Best Buy? These questions come up all the time. We need policies to think about them, and so it's, you know, besides things that Google's interesting in its own right, these are important questions. Okay, Google advertising. So most of Google's revenues come from sponsored links. Often on pages there are no ads at all, but on commercially relevant pages there can be up to 11 ads. I've just got a few examples here. This works better if I do Control 2. So here's a sample Google, what they would call a white page. At Google, I type in a fairly non-commercial word like math counts. You type in math counts, there's just certain, you know, the first thing that comes up is mathcounts.org, and then there's several other things. There are no advertisements there. I type something slightly more commercial, math counts preparation, and one ad has appeared. Later. You can see right there, this is an advertisement it's colored differently than what you see how the color is shown on the screen. There's one advertisement there. I go to a more commercial word. Shorts is a great example of a word that's very hard for Google to know what to do with. Now there are 11 ads. So there are 3 ads here at the top of the page. There are 8 more ads down the right side of the page. One thing you'll notice is that the ads on this page also seem to do a fairly good job. That, you know, the shorts tell you things that, you know, you can buy shorts at Macy's, you can go to Victoria's Secret. Over here there's sort of a Docker site, you know, Docker sites. And then if you go to the sponsored links, Google actually has a little bit of trouble figuring out what you can do with the word shorts. So the number one thing to do is maybe you're interested in short movies, Internet Movie Database, and then they just sort of have these things that look like sort of random links to me, like, you know, I can't imagine that many people really want to buy shorts at Kohl's, but maybe it looks to them like it is. And then the worst link in the world down at the bottom, if you look at the Wikipedia entry, which is just Shorts are a bifurcated garment worn by both men and women over the pelvic area, circling the waist and covering the upper parts of the legs. I mean, I can't imagine that anyone who did this search wanting to know that. But that's what Google picked out. Here, just I'm going to show you the most profitable word to advertise on Google, mesothelioma. Turns out that many people exposed to the rare form of cancer that you get if you've been exposed to asbestos. If you do get mesothelioma, you sue makers of asbestos and you resettle it with them for some large sum of money. So each of those ads there will cost in the hundreds of dollars per click. So if you go there, I click on www.lawfirm.com/mesothelioma law firm, hundreds of dollars just flow to Google. And why will these firms pay this? Well, because if you get a 25% legal fee on a $500,000 settlement, you make a lot of money every time you get a client who has mesothelioma. Okay, how does Google advertising work? One of the keys to Google advertising is that what you want to do is you want to charge $100 per click on mesothelioma. You want to charge 50 cents a click or $1 a click on shorts. You have this sort of, in some sense, there are billions of unique searches done every year on Google. You need to figure out billions of prices. If you had just tried to do this by just naming a price for every page, you never would have thought of the right prices. Right? Who would have thought that mesothelioma was worth hundreds of dollars a click? You just need, there's so many words, so many prices. You need, sort of Google system came up with a sort of auction system that was designed to figure out how people should bid. So it's a remarkable engineering feat. Basically, every time you do Google search, in between the time you do your Google search and the results come back, an auction has been conducted to decide who it is whose ad should get displayed. And here's sort of the mechanics. So advertisers submit standing per-click bids for search queries. There's a fairly expressive bidding language. I can say, I want my ad displayed if someone types exactly the word shorts, or any phrase containing the word shorts, or any phrase containing the word shorts but not containing the word stories or movies, or any phrase containing the word shorts typed by someone in the state of Rhode Island. But you have this fairly expressive bidding language of all the bids that you want to place if that search ever arises. Okay. When someone types a query, in this first engineering challenge, Google has this enormous database of standing bids. They have to identify which of these bids actually apply to this query, and they have to do it in a millisecond. Well, when they do that, they identify all the applicable bids. Right now, I'll just sort of say there's bids B1 through Bn. Google then evaluates the bidders and assigns each bidder a quality score. I've come back to those only in the last 5 minutes, but these quality scores, one for each bid. And then they rank the bids on the product of the bid itself and this quality score. And if, for convenience, let's assume they actually were in order, that B1, W1 is bigger than B2, W2, then they choose bidder 1 to be the winner, and bidder 1 gets the top. And then they choose bidder 2 to be the second winner, bidder 2 gets the second slot on the top, bidder 3 gets the third on the top, bidder 4 gets the first one on the right side, and they go down up to 11 bids. Sometimes they declare there would be fewer than 11 winners. I'll also come back to that later. And then advertisers, the payments. On a Google ad, you pay only if your ad is clicked on. So I get my thing that says mesothelioma up there. If a person doesn't click on my ad, I don't owe Google anything. If Google clicks, I have to make a payment to Google for every click on my ad. What's the payment I make? Well, this is the formula. I pay BK plus 1, WK plus 1 divided by WK. You can think of this, if the weights aren't there, as just being I pay the next highest bid. So if I bid $10, someone else bids $3, every time I click, I pay the 3. I don't pay the 10 that I bid. Okay. And that's the bidding rule. Question is now, for an economist is, how does this work? Why does this work well? If you're just going to think about a question, how does this work well? Does it work better than any other system? What are we concerned about Google's market power here? If Google goes from a 60 share to an 80 share, how's their prices going to change, or are consumers a bit worse off? It's a complicated system, and so what game theorists are going to try to do is think about, how can I think about this game and think about a world in which this mechanism is used to understand what are its properties, why does it work well, and are there things we should be worried about this mechanism. So as an economist, the first thing I would do starting this is I go back to sort of what I learned in economics class, which is one thing that economists have talked about for a long time is solving what are called allocation problems. An allocation problem is you have a set of scarce resources. You have to give them to some subset of the people there. And you have to decide who to give the resources to. And the classic formation of this is, I want to sort of discern, I've got sort of a set of scarce resources, I need to choose an efficient decision out of some set. Okay? So two examples that might be familiar, you know, two students who are trying to decide whether to buy a TV. Each student knows how much the TV is worth to him. So let's suppose this new flat screen TV costs $600 and the students are trying to decide whether to buy a $600 TV. Obviously, what you want to do is buy the TV if V1 plus V2 is bigger than $600 and don't buy the TV if V1 plus V2 is less than $600. You can ask, is there some mechanism that lets us do this? Because many mechanisms you work won't work. You know, so you might think, how a mechanism we each say is worth 300 to us, and then if it's worth 300 to each of us, then we buy it. But that mechanism fails if it's worth 400 to person 1 and 200 to person 2. And you might think, okay, well, why don't I just have each of them say how much it's worth to them, and if they add up to more than 600, then we'll buy it, and each person will pay what it's worth to them. But then obviously, you know, if it's worth 500 to me and I know it's worth 400 to you, I might say, okay, it's worth 200 to me, so you pay the 400, I'll pay the 200. And so it's, you know, anyway, it's not immediately obvious that there's an answer to this mechanism of how can we get people to tell the truth and reach the right decision. Another example, you know, just 3 students have been given 2 tickets to go to some sporting event. Is there some mechanism that they can use to decide which 2 of the 3 should go? And again, you know, you can imagine people make announcements, money changes hands. Somehow, can the 3 of them pick out which 2 should go? And you know, you can even imagine here it might be that people don't even just care about going to the game itself. They might care about who they go or who they go with, or it might be that I want to go and I don't want him to go, or even if he's going alone, I don't want him to go, or you know, the people could have preferences, and how can we pick out the thing that maximizes everyone's preferences? Okay. Anyway, it's a very famous problem in economics. Let me give you a mathematical formulation. So suppose I have n players. N players are going to have what I call utility functions, UI, that depend on 2 things. One is a decision D. There's a single decision D that has to be taken collectively. And the other is a variable theta I. Theta I is a characteristic of player I that's known only to player I and not to the other players. So we're trying to maximize this sort of sum of UI of D comma theta I. The difficulty is each player knows theta, his own theta. He knows how much the TV is worth to me. He doesn't know how much the TV is worth to everyone else. He doesn't know how much everyone else cares about going to the basketball game. Challenge is, can we define a game which has the property that when players play the game, the outcome is the efficient outcome, and perhaps some money changes hands, which is kind of always defined. Turns out there's a very famous theorem in economics called the Vickrey-Clark-Groves theorem that says, yes, there is a solution. There's one caveat about payments I'll get to later, but here's a game that actually produces the efficient outcome all the time. So the game is every player just writes down their true preferences, what is their theta I, which would consist of writing down how much do I value the TV at, or how much utility do I get from going to the game with Bob, how much do I get from going to the game with Sam, how much utility do I get if Bob and Sam go together, how much do I get if Bob goes alone, whatever. I just write down all my preferences. We then look at the preferences and we take the decision that would be best given the stated preferences that everyone wrote down. And then here's the key, is the payment formula. What's the payment formula? Payment formula is everybody is then required to make a payment. Payment is 2 terms. It's this first term minus the second term. You can think of theorem is, I'll give you a second, theorem is if players use this mechanism, then announcing your true information is a dominant strategy. That is, regardless of what the other players do, announcing your payoff is always weakly optimal, and it's strictly optimal in some cases. So truth-telling is at least weakly optimal, therefore this mechanism implements the optimal decision. What is that T function there? I think I have that more on the next slide. Required payment is 2 things. The first term is basically what utility would everybody else other than you get if you weren't around and they just did what was best for them. So either the roommate bought the TV on his own or not, the other 2 guys figured out whether they wanted to go to the games or not, and they just did what was best for them. So the left is what utility everyone else gets if you're not there, messing things up. The right is what utility everyone else gets after after you've said my type is theta 1 hat, and therefore we should do what's in my interest also. Okay? So you can think of this as, this whole thing is just how much have you hurt everyone else by altering the decision that was made. So compare to the decision that would have been made collectively by everyone other than you, compare to the collective decision now that you're there, add up how much you've hurt everyone else, or maybe helped everybody else. That's your payment. So if that's a positive number, you make a payment. If that's a negative number, money flows into you. Okay? And intuition for why I could write out a simple algebraic proof that this mechanism works, but it's not what I want to focus on today. But basically the intuition for this is that this is sort of a fundamental principle of economics, is that everyone doing what's best for them maximizes social welfare unless people are hurting other people by the actions they take with their scarce resources. And so, but once you have everyone pay for all the damage they do to everybody else, you're back to the sort of world where we know selfish economics works fine. And so just putting in these payments that you pay for any pollution you cause, you pay for any damage you do, you pay for any scarce resources you use, then the world works fine in the sort of selfish model is fine. So that's sort of why this mechanism always works. In like the ticket example, if people just had preferences over how much it was worth it to them to go to the game, they didn't care who they went with, the mechanism's very simple. The players would just each sort of write down how much it was worth it to them to go to the game, and then if the numbers were V1, V2, and V3, and V3 was the smallest, then person 1 would pay V3, person 2 would pay V3, and person 3 would pay 0. And you can see, if you think about that, like person 1, basically, they're always paying V3, so I can tell the truth because if I sort of say it's only worth 50 to me or only worth 100 to me when it's really worth 200, it doesn't affect my payment as long as I'm bigger than V3. So anyway, the ticket example, that payment scheme solves the ticket allocation problem. One time why people don't like VCG mechanisms is, one property the VCG mechanisms don't have is they're not what's called budget balanced. It's not the case that transfers can also be made to sum to 0. There's an impossibility theorem that says you can't give everyone the correct incentives and make the payment sum to 0. In some sense, the VCG payments are the only payment scheme that always makes the incentives work out right. But from the Google perspective, this is actually sort of one of the nicer features about Google. If you think about using a VCG mechanism to allocate advertisements, you'll notice that all the payments here are positive and none of them are negative. So that's basically just money flows out. So in this roommate game, you use a VCG mechanism, money flows out of the roommate population. If you imagine using VCG to sell advertisements, money flows out of the advertiser population. Where is it going? You can think of it as going into a black hole sometimes, but here it works fine that the money goes to Google. So just these tickets go out, everyone makes these payments, and then the money flows out of all of them, and then Google just sort of collects that money. So anyway, if someone had first asked the comments, well, how should you allocate advertising? I said, well, we should use something like a VCG mechanism. You just have the advertisers tell you what they would like to pay to be on the screen, and then you take the money and you sort of set up VCG payments, and we just tell you what it is that's worth to be there. Okay? This is not what Google's doing. If you think about the VCG mechanism is very demanding on the bidders, in that, like, think about you have n advertisers or 11 spots on the screen. There are NP11 possible places where the ads could end up. VCG would say, ask every advertiser to submit a vector. What's your utility for each of those n factorial over n minus 11 factorial possible outcomes? You tell me all of those, and then I'll run the VCG mechanism to it, which is, it's difficult both because, I don't know, right, that's just a big number, and I have to, in fact, know what the n is, and have to know who all the other advertisers are, and have these very expressive preferences. That's clearly not what they're doing. They're having everyone submit a scalar, right? Everyone submits just a single number. So to think about what the Google mechanism is doing, what you have to do is write down some model that makes assumptions about the preferences and behavior of the participants. You can't analyze a game without analyzing people playing the game. So to think about this game, what I'm going to do is write down a world in which there are people who have preferences of a particular form, and then let them play this game. The other thing I'm going to do that economists do all the time is also I'm going to simplify the game. Just like in physics, you write down problems with people like throwing balls and stuff. You sort of get air pressure out of there, and you get friction out of the model and stuff like that. Economists, I'm going to do the same thing. I'm going to take it and strip away parts of the game and just focus on this is the fundamental aspect of the game played by my particular people. and think about that problem. So here's my model of the world. Suppose you have n firms. N firms are bidding for M prizes, which I'm going to think of as the M advertising slots. I'm going to assume that prize K consists of getting ZK clicks. So the reason you want to be first on the screen is whoever is first gets Z1 clicks. Z1 is the biggest number of clicks. If you're second, you're going to get fewer clicks. You'll get Z2 clicks. And then as you move further down off the page, you get lower and lower numbers of clicks. And so basically, we just have prizes that consist of clicks. For the utility of the advertisers, I'm going to assume, kind of like in my simple ticket example, all they care about is how many clicks they get. Each advertiser has a different per-click value. So like my per-click value might be 50 cents because 1 out of every 10 times I make a sale, and I earn $5 in profit when I make the sale. So I'm just going to have a linear specification. If I get ZK clicks, I get ZK times VI. Okay, VI is going to be a private information parameter. The bidder I knows how much his value is for a click, but the other guys don't know that. And then now, simplifying Google's game a bit, advertising slots are going to be allocated by a cock auction, which is a simple way of conducting an auction. You have a bidding clock that starts at 0 and just goes up in continuous time. At any point, the bidders can say, I'm out, in which case they drop out of the auction, they leave the world. The clock just sort of rises continuously until there are M people left. If you drop out before that, when there are more than M people left, you're just out. From that point on, the clock rises continuously, and now everybody is guaranteed a slot on the screen. And as the clock is rising, if you drop out, you claim the lowest available slot. Okay? And your payment is going to be the dropout point of the bidder in position K plus 1. So this is trying to capture that Google bidding formula of if the bids are B1, B2, and B3, you win the second slot, you pay B3 per click. So the clock just rises. Every time someone drops out, they get the bottom slot that's still contested. Their payment is the bid of the person below them, and the clock keeps rising to see who's going to drop out and take slot K minus 1, all the way until there's one guy left and he knows he gets the top slot. What happens in this game? Well, it's a fairly simple mathematical object. We can analyze this game, the way we often do games. And simple theorem of this game is the cock auction has a unique Bayesian-Nash equilibrium, which strategies are continuous in the types. In this equilibrium, everybody who loses stays in exactly until the cock reaches their value. Once the cock reaches their value, they drop out. Once bidders have clinched spots on the screen, they no longer bid truthfully. It's not like a VCD mechanism where you just announce your true beliefs. Instead, you shade your bid and you drop out below your value. Where do you drop out? I drop out at this value. I drop out at my value minus ZK over ZK minus 1 times my value minus the next bid. So this term, if you remember here, this was the ratio of the number of clicks I would get in two spaces, and then this is the amount by which my value exceeds the bid at which someone else already dropped out. So this would be what I gain per click if I lose. So what the theorem says is that people don't play the Google game truthfully. What they're going to do is they're going to sort of bid truthfully if they reach the screen, but then once they've got a slot on the screen, they're going to shade their bid less than what the good is really worth to them, or the slot is worth to them. And they bid less by that amount. Intuitively, you've got to shade your bid here because suppose I've clinched a spot on the screen, I'm going to stay in until the bid reaches my true value. Then the worst thing in the world that could happen to me is someone else drops out at V minus epsilon when my value is V. Because then I'm paying V minus epsilon for every click I get, so I'm only getting epsilon profit per click. I would be much better off having taken a smaller number of clicks and a big profit margin. And so as soon as it is I'm afraid of winning, that's when you drop out. You just should not be in a game if you don't want to win. And so once the threshold crosses a point where I'd rather take that losing position at a high profit margin for a few clicks, that's when you drop out. Okay? How would I prove this theorem? The way you analyze many games, the way you analyze chess or tic-tac-toe or anything like that, is you always just start at the end and work your way back. This game, you just do the same thing. Everybody, if you just sort of think about working backwards in time, everyone who's going to lose has to bid their true value because there's no point bidding more than your value. If you bid less than your value, you might as well stay in and hope everyone else drops out. then once we get to people who are winning this auction, this is a game I've written down. Economists often write down things that are everything's infinitely continuously differentiable. It's a modeling device that help you solve things. So when I get to make up how the world works, it's not like physics where the real physical laws. So the payoffs are differentiable. So therefore, if a player is dropping out in equilibrium at B of B star of V, it must be that B star of V maximizes the player's payoff. Therefore, the derivative of his payoff at B star of V is exactly 0, which, to sort of describe this informally, you think of a player is indifferent to first order between dropping out at B star of V and B star of V plus dB for some infinitesimal dB. So I'm indifferent between those two things to first order. Okay. Well, if you think about the Google payment mechanism, it has the property that if I drop out at B or B plus dB, and no one else drops out in between, nothing is different from my perspective. I win, I end up in the same place, and I make exactly the same payment. My payment's the next guy's bid, not my own bid. Therefore, if I'm indifferent unconditionally, and I'm also indifferent conditional on no one else dropping out in between, by the way conditional probabilities work, I must therefore also be indifferent conditional on someone else dropping out between B and B plus dB. Okay, so if I'm indifferent unconditionally, I'm indifferent conditional on no one dropping out, I must be indifferent conditional on someone dropping out. And so that says, I can just sort of basically say, well, if someone else is going to drop out in between these two bids, this would be the payoff I get if I drop out at the lower amount before the other guy drops out. This would be the payoff I get if I drop out after the other guy drops out. I've got to be indifferent between these two. Notice that's a nice simple equation where B star of V only appears one time. I just solved for B star of V. That's the equation that determines an optimal bid shading rule. Okay. So anyway, I've written down the simple world. I've sort of said this is what would happen in this world. Now let's think about properties of this solution I've just derived. One sort of remarkable observation is that in this world I just described, the combination of, there's this Google mechanism which is not the VCG mechanism, and then you have this strategic bidding where people are bidding not, people don't play like a VCG mechanism where you announce your true value. People are instead shading their value in this particular way. But somehow this combination of the Google mechanism plus the strategic bidding results in the exact same payments that you would have gotten with the VCG mechanism. So in some sense, the mechanism's not VCG, the bidding is not truthful, but the two of them together produce the VCG outcome. And how would you see that? Well, losing bidders pay nothing. That's what VCG says they should pay, because they're not hurting anybody by being there as losing bidders. The bidder in the final position on the screen just pays ZM times VM plus 1. Again, that's the VCG payment, because what you've done is the guy in the last position has just bumped one advertiser off the screen. This is what that advertiser would have gotten for being there, because that advertiser was bidding truthfully. And then if you just sort of keep going up, this should say the bidder in position M minus 1. That's a typo, that should be an M minus 1. What does that bidder pay? That bidder pays ZM minus 1 times the equilibrium bid of the person below. But that person below isn't bidding his true values VM, he's instead bidding VM minus something. And then if you just do the algebra for ZM minus 1 times VM minus this, that thing cancels with that, and you end up getting, this is exactly what the bidder in position M minus 1 pays in equilibrium. The first one here, those are the clicks you've taken away from the bidder in position M by bumping him down one spot. He was supposed to get ZM minus 1 clicks, but you bumped him down in position M. He gets this many clicks instead, so these are the clicks he lost, and that's how much those clicks were worth to him. And then I also took the guy who would have been in position M and I bumped him down a spot. That's what he would have gotten, that's what those clicks were worth to him. This is the VCG payment, right? It's just adding up over all the people, what did you get? How many clicks did they lose by you being there? How much were they worth to them? And basically, again, it's a simple inductive argument. Sort of once you've seen it works for 1 and 2, you just show by induction that going all the way up the chain, these are the VCG payments for everybody. Okay? So what Google's basically done is they reinvented the VCG mechanism, but they reinvented it in a way that requires a scalar bid instead of a vector of length n factorial over n minus 11 factorial. But other than that, it appears to be the VCG mechanism. One consequence of BCG equivalence is that this equilibrium is an ex post equilibrium. I derive this equilibrium for everyone drops out, like when they want to lose, they drop out. But anyway, it's a consequence of the argument I just gave that this is what we call an ex post equilibrium. Once you see all the bidding that's happened after you don't want to change you don't want to go back and change your bids. Okay, and that's because the BCG mechanism had that property, and this thing was basically the same thing. So no one wants to change their bids after they've seen what everyone else bid. That's not true in like a traditional sealed bid auction. A traditional sealed bid auction, the painting's worth $100 for me, I write down 50. When I see someone else wins at 60, I want to go back and write down 61. The Yahoo auction had that property. It wasn't an ex post equilibrium. Everyone bid what they wanted to bid, and then once they see the outcomes and they want to change their bids, everyone wants to change their bids over and over again. Google's mechanism has a property that it's an ex post equilibrium. Once you see everyone else bid, you don't want to go back and change what you said. This was a tremendous engineering decision because it meant that people aren't, like it's bad enough people are bidding over 1 billion objects. If people are bidding for 1 billion objects and changing their bids 1,000 times a day, then you have 1 trillion bids a day coming in. But if they're bidding for 1 billion objects and you have people change their bids once a month, then you've got just a few million, tens of millions of bids coming in a day. It reduced the engineering challenges. Third comment is the Google auction mechanism is efficient. Like the BCG mechanism, it's picking out all the bidders who have the highest values for those ad slots and putting them there. Okay? That's a really important property. People often ask me, well, isn't there something fundamental conflict of interest in Google between the fact that they're supposed to provide the best organic links in the world and be honest and provide all the links that you want for free, and yet they're also taking advertising to put things up? Isn't there a conflict of interest there, or don't they want to, isn't there a conflict between, how can I provide the best ads for free and then also charge people for ads? Why wouldn't anyone pay for the ads? Well, the key is that the sponsored links are often better than the real links. Shorts was a great example of that. On math counts, they can pick out the math counts website, that's what people want. On shorts, there are 1 million stores selling shorts. How are they going to know which of those are good short stores or bad short stores? How do they know that Kohl's is sort of unfashionable and nobody wants to buy Kohl's shorts? They can look at the page, Kohl's has pictures of 1,000 shorts. But so Google's algorithmic people think, hey, this is the place to go to buy shorts. Everyone would go to Kohl's. But in reality, how does the sort of algorithmic side figure out that Kohl's is not there on the sponsored search side? Well, there's information available to the sponsored search people that isn't available to the algorithmic people, which is what is Kohl's willing to pay to be there? And Kohl's is not willing to pay much to be there as a sponsored link because people don't buy shorts at Kohl's. And that's information that's available to Google advertising, not available to people who do the left-hand side of the screen. That makes the right-hand side of the screen often better than the left side. And this is sort of what I think of as the sort of brilliant idea here is that there's information that the advertisers have that no matter how good our textual analysis people are, they're never going to be able to figure out who actually sells the shorts. And then putting the bids in there as an extra source of information, Google advertising becomes better than Google regular links, and that's what makes Google advertising work so well. What's also brilliant from a business perspective is many businesses, you have a great business, someone comes in and undercuts you and charges people less and takes your business away. Okay? You can't steal Google's advertisers by charging any less, because this is what the BCG theorem says, is that if you want to get truthful revelation in bidding, you have to charge the people. If you sort of say, I'll only charge you half of what you bid, then people will just bid twice as much. There's no way that you can get people to reveal the information to you of how much the ad space is worth without actually charging them the money, which makes Google sort of relatively immune to competition, that you can't just come in and undercut them, because if you undercut them, you don't get the information about which are the best ads. Okay, end of part one of the discussion. That sort of, that simple model, you might think this is we've now done Google, but it turns out that, this is good for thinking about some questions. It's not good for thinking about other questions about Google. So like these questions that came up of should Google, Google had a deal in place with Yahoo where Google would serve all of Yahoo's searches. The Yahoo search would shut down and Google would just, every time you did a search on Yahoo, Yahoo still has about 15% of the US search market. Every time you did a search on Yahoo, Google would do the search instead and display Google ads instead of Yahoo ads, and Google would just pay money to Yahoo. Right? In many industries, like if Ford wanted to merge with General Motors, we would say, no, you can't merge Ford and General Motors because they have too big a share of the car market, they raise prices. Question came up, should Google have been allowed to serve Yahoo searches, or when Google and Yahoo are searching things, will they raise prices? Okay. Your first thought might be, no, that can't be. There's prices. Google isn't determining prices; it's an auction. So we should throw away our traditional economics that says firms with market power will raise prices. But they think, no, actually, that is a better question. Google isn't just auctioning off things. Google's got one instrument that I left out of that model, which is it chooses how many winners there are. There are not always 11 winners. Like I showed you on that math counts page, sometimes there's only one winner. How is there only one winner? Well, Google sets a reserve price in these auctions. They actually set different reserves. I can ask if you want to know, but basically, if you don't bid above a certain amount, they won't show your ad. So like I could try to buy an ad on that math counts page, and they would tell me, Glenn, if you want to pay 50 cents a click, we'll put you up there. If you're not willing to pay 50 cents, we're not going to show you, even if you're outbidding everyone else for that math counts page. So there's a reserve price, and often there are no winners. Well, if you think about, you could sort of take that model I just did and put a reserve price in to say that everyone not only has to bid as high as the 11th highest firm, they all have to bid at least R to get on the page. And then you could redo that analysis. If you did that, though, you'd reach a very immediate conclusion, which is reserve prices are bad. Right? All reserve prices we do in that model would stand in the way of having ads displayed that it was valuable for firms to display. So social efficiency would say that R should be 0. We should force Google to charge an R of 0. And then any action that lets Google raise their reserve price R would be bad socially. But I think that's also too simplistic an answer because we know Google likes white pages. Google argues that math counts page with all white on it is a very valuable thing that they're doing of not showing any ads because people don't like ads. And that somehow a system with blank pages is better socially because this model here just had two players. It just had Google and it had the advertisers. It didn't have the people who were searching. And so I think to address Google's view of reserve prices, you need a different model. You need a model that has three sides. You need a model that has advertisers, you need a model that has Google, and you need a model that has the people who are actually doing the searching. So that's what I was going to talk about next. I'd like to also argue that it's, I think it's also intellectually interesting to think about the fact that Google is attracting objects. There's a huge auction theory literature about people auctioning off paintings or bottles of wine or whatever, but one thing that's sort of constant in that literature is the objects are objects. And if I change the rules and auction them off with a fixed price or a reserve price or you pay the second highest bid, the bottle of wine never changes. One thing to do about Google auction is the objects actually themselves of your auctioning change. If I change the rules, that's going to, if I change the rules that prevent low quality ads from being shown, then that's going to change what consumers think about the quality of the ads, and that's going to change whether or not they decide to click on them. So in some sense it's an auction, but it's an auction where the objects being auctioned change as you change the auction rules. So I think that it's this area that I think, if you think of there's a big auction literature, this opens up a whole new scope for things. So here is a model I wrote down to try to think about this. And sometimes this is the art of doing game theory and economics, is you just try to think of what model can I write down which incorporates all the things that I think need to be there and which is still simple enough that I can solve it. And sometimes it makes, those who did math contests as a kid, it may sometimes make doing economics a little more like doing math contests than doing math. That is, like, you don't want to write down the problem that has a really, really hard solution that it takes 20 pages of work to get there. What you're always looking for is what's the model I can write down that puts the things I want there, but then still I can do the solution in 2 pages after I've you've seen what the trick is for why the models give the answer it gives. And that's what game theory spent a lot of time doing, is thinking is what's the question that has a really easy answer. So here's my question that has a pretty easy answer. So I'm adding to the previous model a continuum of consumers. What this unit mass of consumers do is they visit search pages, and they visit them actually to see sponsored links. I'm abstracting away from the presence of the left side of the screen. All these consumers have some need, and they're going to get a payoff of 1 if they meet their need. So they have a need like need a pair of shorts. They type in the word shorts, hoping to find a pair of shorts. of the particular style that they're looking for. Consumer J incurs some cost from clicking on a link. So I'm going to assume that these costs are sort of random in the population. There's some cumulative distribution function G that describes them. And what consumers are going to do is they're just going to search optimally until one of two things happen. Either they meet their need by finding the pair of shorts they want, or their expected benefit from clicking again falls below this SJ, which you can think of as like their time cost of clicking, at which point they'll stop. Okay, so I've got this consumer part of the model where what the consumers do is they have rational beliefs, they understand how the world works, they know the firms out there, and they just click until either they find what they want or they decide, I can do the expected value calculation for the likelihood that I'll find them. It's not worth clicking again. So second part of the model, I have n advertisers bidding to be the sponsored links. Each firm has some probability Qi of meeting the consumer's need. You can think of Qi as being the fraction of all shorts in the world that they sell, something like that. Qi is private information, and I'm assuming the firm's ads, like the name Kohl's, doesn't convey any information. Just, every firm just has a different fraction of the good of consumers whose needs they'll meet, and the firms know that, but no one else does. Firms also get a payoff of 1 if they meet a need. You think this is holding prices fixed at the MSRP or something like that, and that's the profit. Search engine, I'm going to have a search engine conduct a GSP auction and display sponsored links. Same model of the Google mechanism I used last time with the increase in cost auction. So basically what I've done is I've just created this thing called a need. I've had consumers try to meet needs, and then, so this consumers have a search problem, the firms payoffs V now come from the queues. So some observations from analyzing this model. Suppose that in equilibrium the bidding is that the highest quality advertisers bid the most. Then in equilibrium the ads get ordered from best ad on top, second best ad on next, and so on. So the ads are ordered by the queues, and therefore what's going to happen is the consumers are going to search top down. So when you know nothing about the ads other than the top one's the highest quality one, you always start with the highest quality ad first. It's got the highest chance of meeting your need, same cost as anyone else to click on. So consumers search top down, and it's kind of a complicated stopping problem because basically every time I click on a link and don't meet my need, I learn that firm, I do Bayesian updating, I say that firm was lower quality than I thought it was. And because these things are order statistics from a distribution, when I learned that the nth order statistic is smaller than I thought it was, that means the n minus first order statistic is smaller than I thought it was. So every time I click and don't meet my need, I'm learning something about the order statistics, and I keep sort of downweighting my view of the quality, and so I stop searching when that order statistic updated for the Bayesian information isn't worth it. But so that's sort of basically what consumers will do, is a top-down mechanism. Notice that in this mechanism, there's several channels by which advertisements affect welfare. One is that picking out the high-quality ads helps consumers find what they need. The other thing is that ordering the ads helps them sort of make their search most efficient and lets them sort of search top-down in the ads you do present them. And then the third important welfare channel is when the search becomes more efficient in this way, consumers are actually willing to search more, because making the search efficient means I know the ad that's displayed is good, which makes me more likely to click. So what can happen here is in this model, it can have the property that displaying fewer ads causes more clicking to occur. Because when I display fewer ads, the consumers know the ads that are shown are good as they click on them. Whereas if I displayed 11 ads, consumers might click on nothing. When I have a rule that only displayed one if it's good, consumers might click once. So it's not at all clear that displaying fewer ads actually prevents trade as opposed to allowing trade. This game is more complicated. Can we solve this game? It turns out you can solve this model just like you could solve the previous model. The algebra is a bit messier, but the structure of the model is sufficiently similar that it has the same kind of solution. That is, everyone bids what they need to bid to get on the screen. Once you get on the screen, you start shading your bid, and your bid is, once I'm on the screen, I bid whatever the guy below me bid, plus the difference between what he bid and what it's worth to me times something with less than 1. So again, this is shading your bid formula. It's a slightly different one, but I just basically bid what I need to get on the screen, and then I start shading my bid and bidding less than what something is actually worth to me. And how much less, it depends on cumulative distribution functions of the search cost distribution. It depends on these expected qualities that come out of the Bayesian weighting, but it's still a formula you can analyze and say this is how you modify that BCG style bidding. Some other theorems, I don't have time to go through them, I guess, the proofs. But one theorem you can show this model is that consumer surplus is maximized at a positive reserve price. And the proposition that goes with that is that, in fact, consumer surplus and social welfare are maximized at exactly the same reserve price. So whatever is good, there's sort of three parties here. There's the advertisers, Google, and the consumers. What's good for consumers, what's best for consumers is actually also best for all three of them together in aggregate. Okay? What's best for Google is not what's best for the advertisers. Google wants a high reserve, the advertisers want a low reserve, consumers want one in the middle, but what's good for consumers is good for the three in sum also. And you can actually sort of derive formulas for what is the optimal reserve price for consumers from that statement. And the optimal reserve price for consumers, like if Google's only going to display one link, this would be the formula for the optimal reserve price. And the formula for the optimal reserve price, so it's the reserve price satisfies, it's the 1/2 of the expectation of the highest order statistic, conditional on the highest order statistic being at least the reserve price R. Anyway, it's a formula, why do we want formulas like this? We want formulas like this because then you could sort of say, I could analyze Google and I could sort of look at Google's reserve price policies. I could try to calculate analogs of these statistics of what are the values of the highest order statistic and think about where are Google's reserve prices relative to what we would think the socially optimal reserve prices are. And to do that, what you just need to do is calculate the sort of CDFs of this Q distribution and think about, are Google's reserve prices too high or too low? It becomes a quantitative question that you can imagine looking at with data. Okay, part 3 in my final 4 minutes. So far, the models that I've discussed provide one explanation for Google's dominant position. That is, I didn't emphasize it, but there's a positive feedback loop to Google in this advertising problem, which is when you have a larger market share, more advertisers are going to sign up for Google advertising because because there's a fixed cost of learning to bid. The payoffs depend on how many clicks you're getting. When you have a larger market share, you get more advertisers. Well, when Google has more advertisers than Bing, Google can therefore pick out better advertisers for each page. And then if advertising is content, on the word shorts, for instance, more advertisers means your content is better, meaning more people want to use Google instead of Bing. And so you get this positive feedback loop that sort of helps the dominant firm out. I think that this positive feedback loop is important. I don't think it's the whole story because if you think about it, Google spends $3 billion a year on research and development. If that feedback story is all that's going on, we don't need the $3 billion a year in research and development. We just live off the feedback loop. Why do we need the $3 billion? This is something that sort of suggests a future topic people are interested in, where the research is still developing is, in practice, where a lot of that money goes is towards those weights. I pretty much ignored those weights so far and just sort of said the weights are just weights. Well, it turns out those weights are just absolutely crucial to getting this thing to work. I'll show you an example of Yahoo before those weights existed. I'm starting to think it's too small. I did a Yahoo search here for Paris Hilton back 2006. What comes up as the #1 link on Paris Hilton? Paris Hilton ringtones. I don't even know what a Paris Hilton ringtone is, but Paris Hilton ringtones is beating out everything else that could be here. One thing that you often find on this is like you go to Yahoo circa 2005 and you just search for math counts. What would be the #1 link on math counts? It would probably be some kind of pornography. You might think, why would that be on Yahoo 2005? Well, the point is, let's suppose you're going to advertise a math book for math counts preparation. How much are you willing to pay per click? Maybe you're willing to pay 50 cents a click because 1 out of every 10 people will buy the book, you'll make $5 off your book. If you put up a thing that says Paris Hilton sex video 1995 on DVD, free shipping, okay? Most people who search for math counts are not going to click on that link. But once they've read the link that said Paris Hilton sex DVD 1999 free shipping and they click on the link, there's a good chance they're going to buy it. If they're going to buy that DVD and make, you make $19 in profit selling that DVD for $19.95, you can make $19. So it's like you can make 50 cents per click on the Math Counts book, you can make $10 on the Paris Hilton sex video. So the Math Count search will get the Paris Hilton sex video. Okay, what's wrong with that? Well, obviously, it's not good for Yahoo. It's not good for Yahoo either. It's not good for Yahoo either, but what happens is, in a pay-per-click auction, you're putting the guys who bid a lot per click up, not the guys who actually get a lot of clicks. So you want to use those weights to weight the people who get more clicks and give them more credit. But that's actually not the only thing you want to do. There's my paper has some reference on this, that there are many other things that you want to do actually differently with those weights. Once you do the minimum weight, it's very hard. In fact, what Google does is, Google just hires 1,000 mathematicians and computer scientists, tells them, come up with better weights. If you think of a better theory of better weights, make those better weights, try them out on your system. We'll run your trial on 1% of our traffic for a month, see if yours beats somebody else's. And what they're doing is making 1,000 incremental improvements every year in their weighting schemes. And you just keep hiring researchers and researchers and researchers. They build better weights. Where does this give Google an advantage? It gives them an advantage in two ways. One is, you can hire more researchers when you've got the $12 billion flowing in. And two is, when you have a bigger market share, you have more data. So you can run more simultaneous experiments. One thing Google can do that Microsoft never can do is, I can run a Slovenia-Slovakia experiment, where I run system A in Slovenia, run system B in Slovakia, let them go on for 3 months, let all the bids reach equilibrium and see which one works better. If you're Google and you're number one in hundreds of countries, you can have hundreds of such experiments going on. If you're Bing and you only work in the United States, you can only have one experiment going on in that variety. So anyway, in conclusion, I think Google's advertising auctions is a remarkable invention. I think I hope from this talk that I gave a sense of this is how you would use game theory to try to think about this invention. I think there are some things we understand about it very well, that its stability in its prices, why it produces good content. I think there are many other things that people will be doing research for years to come and thinking about how exactly should this work. And it's going to be interesting both for people who want to work on the sort of company side of this and for people working on the government or the regulatory side, trying to think about what should we think of all the many things Google's doing and which of them are good and which of them are bad and what should be allowed to not. Okay, thank you very much.
Are there any questions?
In finance, we have the efficient markets hypothesis. And I'm just wondering, do you think, and I don't know that much about Google or tech stocks, but do you think that what you told us today is public information in the public domain and is known by rational investors?
Yes, so I do think what I told you today is known by rational investors. I think it was not appreciated at first. I think, Google was actually a big success since its IPO. I think people didn't fully appreciate how well this advertising system worked and how much it would tend to produce a dominant firm in the long run. I think that probably is pretty well understood by now. Yeah.
So when you're computing, you're maximizing over these utility functions.
Yeah.
You never give a formula. What's the utility function look like?
Sorry, utility functions for who? Or?
Well, you talked about you're maximizing the U of DI theta I.
Oh yes.
What are they?
Oh well, so in the so this is the so in the general VCG mechanism, it gives a solution as a function of those UDs. This is what I'm doing when I make up these models of Google is this is where I'm making up particular utility functions, saying I'm going to think about a VCG environment with this particular class of utility functions and then tell you how it works. And so that's why in the first Google models I said that the advertiser's utility functions were linear functions which were just a product of the number of clicks times a single constant that was private to the firm. So you could have thought of many different specifications for the advertiser's utility, or in this case, in the searcher's utility, and all of those would give you different conclusions. And so that is, I think, what we're trying to do as economists, is think about what's an interesting utility function to put for the advertisers and what would that say. But If I put a different utility function, that whole VCG equivalence would go away. And so you might think about, it's only VCG with those linear utilities times a single unknown parameter. And so anything else it's not. And so that's the thing you might think about. What other utility functions might you assume, and therefore how might you come up with a better mechanism, one would work better for other utility functions? Yeah.
So I have a question about the sort of the regulatory aspect.
Yeah.
Google has infinite resources to throw at their model. The government trying to come up with sort of understanding it from a regulation point of view has very finite resources.
Yes.
Can they remotely, keep up with Google in terms of understanding what's really going on?
Yeah. So they do have a hard time. The government has a very hard time keeping up with understanding what goes on. The one thing that I guess gives the government some chances, and you might argue this is not exactly like, is there is this competing interest group thing where Microsoft hires very expensive economists to sort of write down and describe how the world works and go in and oppose Google when Google wants to do Google Books, when Google wants to serve Yahoo searches. You do worry that sort of the counter arguments will only come up in the cases where there's someone else who opposes it, whereas the government will be hopelessly behind. If it's something that helps Google and also helps all the other big players, whether it's Motorola or Apple or whatever, then we're in trouble. Yes?
So would the government go and actually compute these reserve prices and then tell Google you should make the reserve prices larger or smaller based on whether or not they think it's fair in the market?
So regulating the reserve price directly is something that's not feasible. And so what the government would do is they would have sort of what they call structural remedies, which is you take the things the government does have power over, like the government has power to approve Google's deal to sort of serve Yahoo searches because it's an agreement among competitors which would be questionable under antitrust laws. And so they could just decide our ability is to say yes or no. You can serve Yahoo searches or you can't. Microsoft is not allowed to pay Dell to make Internet Explorer and Bing the default browser and search engine. Google is allowed to pay Dell to make Google Chrome the default browser. And these are kind of things the government at some point decided to ban Microsoft because they felt like from making IE the default browser, they felt it was monopolizing market power. And so I think what the government would have to do is just sort of decide, do we think Google's reserve prices will get too high if we let them do X, and then you prevent them from doing X when you have the authority to do that. But they don't have the authority to regulate Google's reserve prices. Google's not in violation of any law that would let them have that authority.
All right, well,